Testing, can you hear me? Hello, everyone. I am going to be reading the physics book again. Let me just change to full screen. I'm just opening Desmos and Excalibur. All right. So, wait a minute. Hold on. Just putting my character to the side. All right. So, I read units and measurement, vectors, and motion along a straight line. Now I'm going to read about motion in 2 or 3 dimensions. Let me just close this. They will give a complete description of kinematics. We must explore motion in 2 and 3 dimensions. After all, most objects in our world do not move in straight lines, rather, they follow curved paths. Let's just go next. Displacement vector. To describe motion in 2 and 3 dimensions, we must first establish a coordinate system and a convention for the axis. We generally use the coordinates x, y, and z to locate a particle at point P in 3 dimensions. If a particle is moving, the variable x, y, and z are functions of time. Position vector from the origin of the coordinate system to point P is r, so a vector valued function. In unit vector notation introduced in coordinate system and components of a vector r is so the I vector times x, j vector times y, and k vectors times z. Figure 4.2 shows the coordinate system and the vector to point P where where a particle could be located at a particular time t. Note the orientation of the x, y, and z axis. This orientation is called a right-handed coordinate system and is used throughout the chapter. Right-handed coordinate system. So x is my index finger, y is my middle finger, and c is my thumb. With our definition of the position of a particle in 3 dimensional space, we can formulate 3 dimensional displacement. Figure 4.3 shows a particle at time t1 located at p1 with position vector rt1 at a later time t2. The particle is located at p2 with position vector rt2. The displacement vector is found by subtracting the t1 by t2. Right. A satellite is in a circular polar orbit around the Earth at an altitude of 400 kilometers, meaning it passes directly overhead at the north and south poles. What is the magnitude and direction of the displacement vector from where when it is directly over the north pole to when it is at minus 45 degrees latitude? So directly north pole, and then this is minus 45 degrees over here. So we have 400 kilometers up here. You have 400 kilometers up here, but hold on. What is the magnitude and direction of the displacement vector from when it is directly over the North Pole when it is at minus 45 degrees latitude? You use the arc length, right? So the angle when measured in radians. So if theta in radians, then theta show the theta represents how much theta represents how many times the radius covers the arc. So if theta is like this, then this arc over here is pi r. Yeah. Theta varies from 0 to 2 pi. So the entire circumference is 2 pi r. Like part of the circumference is theta times r. So we need the magnitude of this thing, right? What is the magnitude? This is example 4.1. R is 400 kilometers. You have theta here. So arc length, let's say arc length is theta r. And we need to find the arc length. So it covers 90 degrees and another 45. 90 plus 45 is 135. Pi radians is 180 degrees. Pi over 180 radians is 1 degree. Pi 135 over 180 radians is 130 degrees. L is, oops, (135 over 180 pi times it by 400), 942.4. 942.4 kilometers. Why does it keep doing this? It has an altitude of 400. Oh no, wait, I got it wrong. The radius of the Earth, we take the radius of the Earth as 6370 kilometers. So the length of each position vector is 6770 kilometers. 400 is wrong. It's 6770. Then that means this is wrong. 6770. 15951. 15951.4. Set wait. The magnitude and direction of the displacement vector for. Okay, I calculated the arc length. That's not what I have to calculate. I have to calculate this displacement. So let's take this as 0, 0. So R at T1 is, so the components are 0 in the x direction, 6770, 0 in the c direction. There are only two directions. It's a 2D graph, just x and y. You have a 6770 times it by sine 45, 570. I'll just write it here. Gives this one, right? Yeah, that's the. So this is x, this is y. So the y1 is this much. Cos so now what? So this minus this. So the displacement vector is this minus this. 3556.4. This is in the negative direction. This is positive. This is negative. So minus this, minus this. So we have sine minus this minus 6770. Is this correct so far? They got it a little bit different. Cos minus 45. Is it in degrees or radians? Okay, this makes more sense. So we have minus 11,557. Yep. And then if it was cos, minus 4787. All right, all of this was wrong. Brownian motion is a chaotic random motion of particles suspended in a fluid resulting from collisions with molecules of the fluid. This motion is three-dimensional. The displacements in numerical order of a particle undergoing Brownian motion could look like the following in micrometers. So we have this one, change in R1, change in R2. We have R1, then we have R2, we have R3, R4. What is the total displacement of the particle from the origin? We just add them up, right? So 4 minus 3 minus 1, yeah, just left with 2. J plus plus minus, so J is 0. Yep. Then 3 plus 3 plus 1 plus 2 is 9. In the previous chapter, we found the instantaneous velocity by calculating the derivative of the position function with respect to time. We can do the same operation in 2 and 3 dimensions, but we use vectors. The instantaneous vector velocity is now, so the vector is now, this is a vector velocity. Take the position and we derive it. Figure 4.4 can also be written in terms of the components of V. Since Vx, Vy, Vz. And they're each the derivative, their respective derivative. The independence of perpendicular motions. When we look at three-dimensional equations for position and velocity written in the unit vector notation, we see the components of these equations as separate and unique functions of time that do not depend on one another. Motion along the x direction has no part of its motion along the y and z direction, and similarly for the other two coordinate axes. Thus, the motion of an object in 2 or 3 dimensions can be divided into separate independent motions along the particular axis of the coordinate system. To illustrate this concept with respect to displacement, consider a woman walking from point A to point B in city with square blocks. The woman taking the path from A to B may walk east for so many blocks, then north for another set of blocks to arrive at B. How far she walks east is affected only by her motion eastwards. Okay, I get the point. Acceleration vector. In addition to obtaining the displacement and velocity vectors of an object in motion, we often want to know its acceleration vector at any point in time along its trajectory. This acceleration vector is the instantaneous acceleration. It can be obtained from the derivative with respect to time of the velocity function. As we have seen in the previous chapters, the only difference in 2 or 3 dimensions is that these are now vector quantities. Taking the derivative with respect to time, we find, okay, the acceleration in terms of components is this. So taking the derivative of the velocity in each component. Also, since the velocity is the derivative of the position function, we can write the acceleration in terms of the second derivative of the position function. So second derivative in the x direction, second derivative in the y, second derivative in the z. Constant acceleration. Multidimensional motion with constant acceleration can be treated the same way as shown in the previous chapter for one-dimensional motion. Either we showed that three-dimensional motion is equivalent to three one-dimensional motions, each along an axis perpendicular to the others. To develop the relevant equations in each direction, let's consider the two-dimensional problem of a particle moving in the xy plane with constant acceleration, ignoring the z component for the motion. the acceleration vector is, so acceleration in the x direction, acceleration in the y direction. Each component of the motion has a separate set of equations similar to 3.10 to 3.14 of the previous chapter on one-dimensional motion. We show only the equations for position and velocity in the x and y directions. A similar set of kinematics equations could be written for motions in the z direction. So x, Vx average, V is equal to U plus AT. S is, so current position minus initial position is S. S is equal to UT plus half AT square. It's the previous equation, but in one particular direction. Here, the subscript 0 denotes the initial position of velocity or velocity. 4.11 and 4.18 can be substituted into equation 4.2 and 4.5 without the c component to obtain the position vector and velocity vector as a function of time in two dimensions. Figure 4.10 shows a sphere moving with an acceleration of 2.1 meters per second square down a slope of 15 degrees at t is equal to 0. So acceleration is constant, 2.1 meters per second square, 15 degrees down the slope. With the origin of the coordinate system at the front of the launch, her initial position and velocity are 0.75 and minus 50. Her initial positions, example 4.6. We have why is there a minus here? Okay, wait. R0 is 75.0 I minus 50.0 J meters. Initial velocity 4.1 I minus 1.1 J meters per second. What are the x and y components of the sphere's position and velocity as function of time? What are her position and velocity at t is equal to 10 seconds? What are the x and y components of the sphere's position and velocity as a function of time? So acceleration is constant, 2.1 meters per second square. .1 meters per second square. So, S is equal to UT plus half AT square. So X T is equal to X0 plus velocity in the X direction times it by T plus half. We need to find acceleration in the x and y direction, right? Down a slope 15 degrees. Acceleration in the x direction, cos 15. Why cos 15? It's 15 degrees down a slope. Then acceleration of 2.1 down a slope of 15 degrees. Only it's 15 degrees only in the y direction, right? Not in the x direction. Is it the same for sine 15? Hold on, I'm confused. Okay, we are supposed to imagine it as 2D. I think I got the idea. So there's no 3D over here. It's only x and y. X and y. So it's going ahead, it's going in that direction. Down the slope, 15 degrees. So cos 15 gives this, the x component. X is 2.1 cos 15. Zero point 0.1 cos 15 cos 15 2.28444. Just write it like this. Sine 15. So then we have this t square. So in the x direction, this is 75 plus initial velocity is 4.1. It's half of 2.1. Voila. I accidentally pressed Control S. 2.1 divided by 2, 1.05. Cos 15 t square. And then we have the y direction. We have velocity in the y direction, ut plus half at square. So y is minus 50. Hold on, is this right? Why does it start with, shouldn't y be a really high positive value? So, okay, so minus 50. Plus it with velocity minus 1.1 plus it with 1.05. So half ay sine 15 t square. Let's put a box around this. And let's put a box around that. So we got the x and y components of the skier's position, and now we need the velocity. So xt, yt, v square minus u square. 2a t. Hold on. I think I remember it like this. 2a t is equal to v square minus u square over 2a. Is that right? Over, no, it's not t, it's s. S is equal to v square minus u square over 2a. S is the change in velocity. So change in position. But this is not what we are looking for. This is the wrong equation. I want the velocity, the final and initial time and acceleration. Oh, so then I can just acceleration. No, but I don't need the time, right? I think I will have to use the position then. S is equal to e square minus u square over 2a. So x t minus x 0 is equal to vt square minus v 0 0 square ax Then we have 75.0. I think I will only do it in the x direction. 75.0. We have 2 times, and then in the x direction, we have 2.1 cos 15. So 4.2, right? 4.2 cos 15 plus the initial velocity, which is 4.1, and square root all of that. Let's see. So they got the x. Uh, oh, wait, no, time is fine. I tried to skip the time variable. Never mind this. I tried to avoid the time variable. That's why I didn't use that equation. Vt acceleration is Vt minus, since the acceleration is constant, we can do this. And yeah, in the x direction plus v in the x direction, give you v in the x direction, which is 21. Sorry, not 21. 2.1 cos 15 plus 4.1. Yeah. It wasn't supposed to take that long. Projectile motion is the motion of an object thrown or projected into the air, subjected only to acceleration as a result of gravity. The applications of projectile motion in physics and engineering are numerous. Some examples include meteors as they enter Earth's atmosphere, fireworks, and the motion of any ball in sports. Such objects are called projectiles, and their path is called a trajectory. Motions of an if of falling objects are discussed in motion along a straight line. It's a simple one-dimensional type of projectile motion in which there are no horizontal movement. In this section, we consider two-dimensional projectile motion. Right, so he kicks a ball. There's the motion in the x direction, motion in the y direction. To describe projectile motion completely, we must include velocity and acceleration as well as displacement. We must find their components along the x and y axis. Let's assume forces except gravity, such as air resistance and friction, for example, are negligible. Defining the positive direction to be upwards, the components of acceleration are then very simple. So ay is equal to minus 9.8. Because gravity is vertical, if ax is equal to 0, this means the initial velocity in the x direction is equal to the final velocity in the x direction. Or Vx is equal to V naught x. So the velocity doesn't change because velocity in the x direction doesn't change because we are ignoring air resistance. Velocity in the y direction will change because of gravity. The kinematic equations for motion in a uniform gravitational field become kinetic equations with Ay is equal to minus g. During a fireworks display, a shell is shot into the air with an initial speed of 70 meters per second at an angle of 75 degrees above the horizontal, as illustrated in figure 4.13. The fuse is timed to ignite the shell just as it reaches its highest point above the ground. Example 4.7. Calculate the height at which the shell explodes. So the fuse is timed to ignite the shell just as it reaches the highest point above the ground. Didn't they just show the height? So the highest point is 233 meters. Well, they just gave the answer. Well, let's just calculate it anyways. Initial speed is 70 meters per second at an angle of 75 degrees. 75 degrees. This is not 75. 75 degrees. So um, the the initial velocity is 70 meters per second. So Vx 75 degrees. 70 cos 75. Vy is 70 sine 75. Dh is uh, when firework reaches highest point. So velocity y. Dh is 0. Acceleration in the y direction is minus 9.8 1 meters per second square. And then we have uh, the later velocity plus the initial velocity. And time h minus 9.81. We have this as 0, this as this as a 70 sine 75 or dh. dh is equal to sine 75 divided by, what was it again? 9.81. 6.89. 6.89. You have three significant figures, so I think 6.89 is valid. This is the time we need to calculate the height. So the change in position in the y direction is So this square square 2ay. So this is 0. This is minus 70 sine. This is a square. 9.81. 2 times this. Then we have this square. 233 meters, which is what we got. How much time passes between the launch of the shell and the explosion? Should be around 6.9. Why do they write 6.90? And what's the last one? What is the horizontal displacement of the shell when it explodes? I mean, they gave the answer here, but we will calculate it anyway. So the velocity in the x direction is constant and it goes on for 6.89. So we have this, right? Let's call it TH. So we have velocity in the x direction, 70 cos 75. 70 cos 75 times it by TH 124. Yeah, 125. So the change in position in the x direction, displacement in the x direction, this gives us 125 meters. What is the total displacement from the point of the launch to the highest point? So this square plus this square and then square root, right? Yeah, the total displacement. Yeah, this square plus this square and square root all of that. You got 264 meters. Time of flight trajectory and range of interest are of interest are the time of flight trajectory and range of projectile launched on a flat horizontal surface and impacting on the same surface. In this case, kinematic equations give useful expressions of these quantities, which are derived in the following sections. We can solve for the time of flight of a projectile that is both launched and impacts on a flat horizontal surface by performing some manipulations of kinetic equations. We know the position and displacement in y must be 0 at launch and at impact on an even surface. Thus, we set the displacement in y equal to 0 and find this. So we have s is equal to ut plus half at square. So that equation, you plug it in here, they got this. Uh, so they took the t out. Wait, I don't understand what's happening. Solving for t gives us this. So t is either 0, which will output 0, or this term needs to be 0. If this inside term needs to be 0, yeah, then t would be equal to, yeah, now I understand. This is time, the time of flight for a projectile launch and impacting on a horizontal surface. Example 4.24 does not apply when the projectile lands at a different elevation than it was launched. As we saw in example 4.8 of the tennis player hitting the ball into the stands. The other solution, t is equal to 0, correspond to the time at launch. The time of flight is nearly proportional to the initial velocity in the y direction in inversely proportional to g. Thus, on the moon, where gravity is 1/6 that of the Earth, the projectile launched at the same velocity as on Earth would be airborne 6 times as long. The trajectory of a projectile can be found by eliminating the variable t from the kinematic equations for arbitrary t and solving for y. And they end up with y is equal to. So they are trying to find what? So the projectile is launched from the origin. So they're finding a y position at a particular x position, right? Yeah, so I think what they're trying to do is like we have motion like this. So for a given x position, they want to find the corresponding y position. And it's parabolic. From the trajectory equation, we can also find the range or the horizontal distance traveled by the projectile. So the range is, these are not the equations I memorized during my A levels. So they started with this, the position. Okay, so by range, they mean y 0 and then goes up and y 0 again. So we have to find two values where y is 0. The first one is when x is 0. The second one is when x is a large value. So x is either 0 or x is some large value, some other value. And this some other value is over here. 2 u squared sine cos over g. Corresponding to the impact point using the trigonometric identity, 2 sine cos is equal to sine 2 theta, and setting x is equal to r for range, we find, okay, so 2 sine cos, they changed it to sine 2 theta. So u square sine 2 theta over g is the range. These are some, okay, this one is useful and simple. This one could be useful. So time of flight 2. So the time all the way from this y0 all the way till this y0. To u sine over g. We have tan x minus g over 2v cos x squared. Should I do one exercise? A golfer encounters two different situations on different holes. On the second hole, they are 120 meters from the green and want to hit the ball 90 meters and let it run onto the green. They angle their shot the ang- they angle the shot low to the ground at 30 degrees to the horizontal to let the ball roll after impact. On the fourth hole, they are 90 meters from the green and want to let the ball drop with a minimum amount of rolling after impact. Here, they angle the shot at 70 degrees to the horizontal to minimize rolling after impact. Both shots are hit and impacted on a level surface. Okay, so this is example 4.9. On the second hole, a golfer encounters two different situations on different holes. On the second hole, in 120 meters from the green, and want to hit the ball 90 meter and let it run onto the green. You want to hit the ball 90 meter and let it run to the green. They angle the shot low to the ground at 30 degrees to the horizontal to let the ball roll after impact. On the fourth hole, they are 90 meters from the green and want to let the ball drop with minimum amount of rolling after impact. Angle the shot at 70 degrees to the horizontal to minimize the rolling after impact. Both shots are hit and impacted on a surface level. So they're both hitting at 90. Okay. So I think this is what's happening. They both hit at 90. And what we are supposed to calculate, well, I already saw the answer, but I haven't calculated anyways. One is theta 1 is 30. It's to 70 and 30. Or let's do 30 first and then 70. It doesn't make a difference. What is the initial speed of the ball at the second hole? Second hole. This is the third. Second hole. I don't know. I don't get what they mean by second hole, fourth hole, or rolling on the green, whatever. Initial speed of the ball at the fourth hole. Initial speed at the second hole. We have y, we have time of flight, y, and we have range. So we need this to be 90. The angle is 30. I think we are supposed to use the time of flight. Or maybe not. We have the acceleration, we have the displacement, we have the angle. Okay, so we have the v in the x direction, t. This will be constant. I'm confused. Hold on. V naught sine theta. This v naught is the overall v naught, right? The speed, not the velocity. Let me think. If that's the time, s is equal to. Now I need an equation where the velocity is not considered. Hold on. I think we are supposed to use this. The range is 90. So the range is u squared as the initial speed, theta 1. So the range, no, the range will always be 90. I will just initial speed 1 over g 90, 9.81 sine 30 square root square root 90 sine 30 sine 2 times 30 sine 2 times, so this is sine 60. 9.81. But the g could be negative, right? This could be minus g. Also, I have to divide it, not multiply it. To divide it by sign. So divided by sign. The range x 31.929, 31.9. But why does it say 9.8 and not? Did the negative part cancel out? Did they take the negative part into account already? Normally, this is plus. Is the negative included in the g? It's not, right? The g is just like this. Then we have 31.929. 929. And same for the other velocity. Write the trajectory equation for both cases. So we just map this, right? Uniform and non-uniform circular motion. Uniform circular motion is a specific type of motion in which an object travels in a circle with a constant speed. For example, any point in a propeller spinning at a constant rate is executing uniform circular motion. On one-dimensional kinematics, objects with constant speed have zero acceleration. However, in two and three-dimensional kinematics, even if the speed is constant, a particle can have acceleration if it moves along a curved trajectory, such as a circle. In this case, the velocity vector is changing. So dv over dt. This is shown in figure 4.18. So we have a velocity over here. So the instantaneous change in r gives the velocity, and the instantaneous change in r plus at time delta after delta t would give this velocity. This is the change in velocity. As a particle moves counterclockwise in time t on a circular path, its position vector from r to r t plus delta t. The velocity vector has a constant magnitude and is tangent to the path as it changes from v to the other v, changing its direction only uh, since the velocity vector is perpendicular to the position vector. Triangles formed by the position vectors and delta r and the velocity vector delta v are similar. Furthermore, change in r. No, wait. The yeah position. This is the radius, right? And this velocity is equal to this. Wait a minute. I'm not really sure about this part. Unless the acceleration is constant. No, no, unless the speed is constant. We can find the magnitude of the acceleration from this. So limit delta t all the way to 0. We get v over r, limit delta r over delta t. Um, how did they get this? So the limit as delta t goes to 0 is delta v over delta t. From these facts, we can make the assertion. But I don't understand this part. How is velocity over here equal to velocity over here? Are we assuming that the speed is constant? The velocity vector has a constant magnitude and it's tangent to the path as it changes from v to vt plus delta t. The velocity vector has a constant magnitude. So we made the assumption that we are talking about a case where the magnitude of the velocity is constant. From these facts, we make the assertion delta v, so this over here, delta v over v, what? Delta v over v is equal to delta r over r. Delta v over v is equal to delta r over r because these triangles are similar. Or delta v is equal to v over r delta r. Okay, so that's how they got this. And then we got v square over r. R is the position, right? The direction of the acceleration can also be found by noting that as delta t and therefore delta theta approach 0, the vector delta v approaches a direction perpendicular to v. In the limit delta t goes to 0, delta v is perpendicular to v. Since v is tangent to the circle, the acceleration points towards the center of the circle. Summarizing, a particle moving in a circle at a constant speed has the acceleration with magnitude this. The direction of the acceleration vector is towards the center of the circle. This is the radial acceleration and is the centripetal acceleration, which is why we give it the subscript c. The word centripetal comes from the Latin word centrum and peter, which means to seek, thus meaning center seeking. A jet is flying 134.1 meters per second along a straight line. It makes a turn along a circular path level with the ground. What does the radius of the circle have to produce? What does the radius of the circle have to be to produce a centripetal acceleration of 1 g on the pilot and the jet towards the center of the circular trajectory? So this needs to be a 1 g. What is the radius? So we know the velocity, we know the magnitude of the velocity, we know g is 1. So if we do 134 square, that should be the radius. Oh, 1 times g is 9.8. 134.1 square and divided by 9.8. Equations of motions for uniform circular motion. A particle executing circular motion can be described by its position vector r. Figure 4.20 shows a particle executing circular motion in a counterclockwise direction. As the particle moves on the circle, its vector sweeps out the angle theta with the x-axis. Vector r making an angle theta with the x-axis is shown with its component along the x and y-axis. Magnitude of the position vector is a is equal to length of r and is the radius of the circle, so that in terms of its components we have this. This is the magnitude cos I and a sine j. Right. Where is it? So we have a so we have a, and then this part would be a cos theta, and then a sine theta. And they said constant speed. Is the speed still constant? The particle moves on the circle, its position vector uniform circular motion. Oh, the speed is constant. So the speed is constant. So like the position, the particle on the circle, it goes around the circle at a constant speed. Here, omega, this is omega, right? Is a constant called angular frequency of the particle. The angular frequency has units of radians per second. So radians per second. And is simply the number of radians of angular measure through which the particle passes per second. The angle theta that the position vector has at any particular time is omega t. If t is the period of motion or the time to complete one revolution, 2 pi, then omega is the angular frequency is 2 pi over t. All right. So omega times t both together gives the radiant. Velocity and acceleration can be obtained from the position function by differentiating. The velocity, we have minus sign. Oh, velocity with respect to time. You have a omega sine radiant and then a omega cos. This is omega, right? Hold on, let me. Okay, never mind. Hold on. Yeah, it is omega. It can be shown from figure 4.2 that the velocity vector is tangential to the circle at the location of the particle with magnitude AW. Sorry, A omega. Similarly, the acceleration vector is found by differentiating the velocity. Wait, if you want the magnitude, yeah, this part square plus this part square and square root the whole thing. Sine plus sine square plus cos square gives 1. So the square, so A and omega remains and square root cancels out. So A omega is the velocity. Similarly, acceleration vector is found by differentiating the velocity. From this equation, we can see that the acceleration vector has magnitude A omega square and is directly directed opposite of the position vector towards the origin. Because acceleration is minus omega square r. Right. So it's the position velocity in the negative direction. Circular motion does not have to be at a constant speed. A particle can travel in a circle and speed up or slow down, showing an acceleration in the direction of motion. In uniform circular motion, the particle executing circular motion has a constant speed and the circle is at a fixed radius. If the speed of a particle is changing as well, then we introduce an additional acceleration in the direction tangential to the circle. Such acceleration occur at the point on a top that is changing its spin rate or any accelerating rotor. In displacement and velocity vectors, we show the centripetal acceleration is the time rate of change of the direction of the velocity vector. If the speed of the particle is changing, then it has tangential acceleration, that is the time rate of change of the magnitude of the velocity. The direction of the tangential acceleration is tangent to the circle, whereas the direction of the centripetal acceleration is radially inwards towards the center of the circle. Thus, a particle in a circular motion with a tangential acceleration has a total acceleration that is the vector sum of the centripetal and tangential accelerations. The acceleration vectors are shown in figure 4.22. Note that the two acceleration vectors AC and AT are perpendicular to each other, with AC in the radial direction and AT in the tangential direction. The total acceleration A points at an angle between A and C and T. Um, all right. So now the acceleration isn't really pointing here, it's more pointing to the left. Total acceleration during circular motion. A particle moves in a circle of radius 2 during the time interval t is equal to 1.5 to t is equal to 4. Its speed varies with time according to this. What is the total acceleration of the particle at t is equal to 2 seconds? So now we plug in 2 over here. So 4 minus 6 over 2 square. 4 minus 6 over 2 square. We have 2.5. So velocity at that point is 2.5. But the change in velocity is we have 4.12. So derivate this with respect to t, it's 0. And then we have minus c2. This is the tangential accelerations minus c2, which is minus 6. But yeah, we got this. But what about the centripetal one? We have the radius of 2 meters, right? The centripetal one would be these are for uniform motions. Now this is for uniform motion. Right, how do we wait when they derived v squared over r? It was for uniform motion, right? Yeah, uniform circular motion. Can we use this if the velocity is changing? Can we still use this function? Okay, they got the centripetal one, and then they calculated this. Okay, I need to understand the last bit, why they're using this function here. Okay, I will just, I need to leave. I will just read this and then I will leave. To discuss relative motion in one or more dimensions, we first introduce the concept of reference frames. When we say an object has a certain velocity, we must state it has a velocity with respect to a given reference frame. In most examples we have examined so far, this reference frame has been Earth. If you say a person is sitting in a train moving 10 meters per second east, then you imply the person on the train is moving relative to the surface of the Earth at this velocity, and Earth is the reference frame. We can expand our view of the motion of the person on the train and say the Earth is spinning in its orbit around the Sun. In which case, the motion has the motion becomes more complicated. In this case, the solar system is the reference frame. In summary, all discussion of relative motion must define the reference frames involved. We introduce relative motion in one dimension first, because the velocity vectors simplify to having only two possible directions. Take the example of a person sitting in the train moving east. If we choose east as a positive direction and earth as a reference frame, then we can write the velocity of the train with respect to the earth as uh, VTE is equal to 10 meters per second I east, where the subscripts TE refer to the train and earth. Let's say now the person gets up out of her seat and walks towards the back of the train at 2 meters per second. This tells us she has the velocity relative to the reference frame of the train. Since the person is walking west in the negative direction, we write her velocity with respect to the train as minus 2 meters per second. We can add the two velocities to find the velocity of the person with respect to Earth. The relative velocity is written as this. So the train goes relative to Earth 10 meters per second. Person goes relative to the train minus 2 meters per second. The person is going relative to the Earth positive 8 meters per second. And then we have this in the two directions. Now apply this concept to describe motion in two dimensions. Consider particle P and reference frames S and S delta as shown in figure 4.26. The position of the origin of S delta as measured in S is R S apostrophe S. Position of P as measured in S apostrophe S R P S apostrophe. The position P as measured in S is RPS. All right. Okay, there wasn't much in this chapter. So we have RPS is equal to RPS apostrophe this plus RS apostrophe S. This plus, yeah, this plus this because I think this frame of reference is moving. All right. I really skimmed through that chapter. All right, I will end the stream here. And the next stream, I will start studying the next chapters. Anyways, see you guys next time. Bye.